Welcome back, deep divers. Ready for another fascinating deep dive? Today we're going to be looking at a research paper that has really piqued my interest.
Ooh, I like that. Piqued your interest.
Yeah, it's about how deep neural networks can learn syntax, the rules of language.
Mm.
But here's the kicker. They learn it just from raw audio,
hmm
like no text at all.
That is super interesting. You know what's really cool about this is it's not about building robots that can have a conversation with us. It's about something much, much deeper. It's
Mhm.
about trying to understand how we developed language in the first place. Like, how did humans evolve language?
I see. So imagine these networks just start spontaneously putting words together into combinations they've never even heard before. The researchers call it spontaneous concatenation.
Yeah, and that's kind of like that stage where babies go from babbling single sounds to suddenly, stringing words together.
Right.
And this research might actually give us clues about how that kind of amazing leap happens, not just in babies, but also potentially in like how language itself actually evolved.
Wow. So to kind of simulate how our brains might learn from sound, the researchers use a network that's really good at recognizing patterns, kind of like the auditory cortex in our brains.
Exactly. And they trained these networks on a massive, massive database of spoken English. But the trick here is how they structured the learning process. It's kind of like, imagine a game where one part of the network is trying to create these realistic speech sounds,
Okay.
and then the other part is acting like a judge, right? And that judge is deciding, are those sounds real or are they fake?
Ah. So it's learning by going back and forth, and just trying to get better at, mimicking real speech.
Exactly. And that's where it gets really, really interesting. So in the first experiment, they took the network and they fed it single words.
Okay.
Like, suit, year, water,
Yeah.
simple stuff, right?
Table, yeah.
But then they tweaked the code just a little bit.
Okay.
They introduced these things called negative values, almost like they were throwing a wrench into the works.
Oh, so they messed with the code a little bit.
Mm.
So did that break everything?
It's funny you should say that because that's what I thought was going to happen. But quite the opposite. Instead of breaking down, the network started producing two-word outputs.
What?
Like suit year. It was like those negative values unlocked some hidden potential and allowed the network to actually combine words in ways that it hadn't done before.
So they kind of messed with the code and accidentally stumbled upon a way to make it combine words.
Mm.
That's wild. But was this just a one-time fluke?
Well, to make sure it wasn't just a fluke, a lucky accident, they repeated the experiment with all these different models. They even added like random data just to make sure there wasn't some weird quirk in the original setup. And guess what? They kept seeing the same thing. The more they pushed these negative values, the more likely the network was to just spit out these multi-word combinations.
So it was like they found a secret doorway in the code, a secret doorway to combining words. And to prove it wasn't just, limited to certain words, they make sure all the training words popped up in these new combinations, right?
Absolutely. It wasn't like, suit always came first or anything like that. All the words they trained the network on, they got all mixed and matched in these two-word outputs. They even got one that was a three-word combination. Box underwater.
A box underwater. Wow. Okay, this is starting to sound a lot like language. So how did they go from these kind of, I guess, random combinations to something a bit more meaningful? That's where experiment number 2 comes in, right?
Bingo. So this time they decided, okay, let's train the network on both single words and some two-word combinations. But they left out one very specific combination.
Okay, which one?
Suit greasy. And the question was, could the network fill in the gap?
Oh, okay. So I'm on the edge of my seat. Did it manage to come up with suit greasy?
You bet it did. And you want to know the interesting part? It happened most frequently when they used those negative values in the code.
Huh. So it's like the network kind of realized, hey, something's missing here. This logically fits. Let's try it out.
Right. And it gets even more interesting. Beyond just these simple combinations, they started to notice something else emerging: repetition. The network started producing outputs like greasy, greasy, even though that never appeared in the data.
Wait a minute. So not only was it just like stringing words together, it was starting to play with them. It was experimenting with repetition, almost like
Almost like a child. Think about it. When kids are learning to talk, you hear them repeating words all the time. Mama, mama, car, car.
That's right, right.
And this kind of repetition, it's called reduplication, is a common feature in language development.
Wow. So the network is not only combining words it's never heard before, but it's also spontaneously using, a strategy that's common in human language development.
That's crazy. Okay, so earlier you said that these negative code values are like throwing a wrench in the works. But it seems like they're doing a lot more than that. What's really going on here?
Well, the researchers believe it has to do with a concept called disinhibition. It's a little bit of a brain twister, but bear with me because it's totally fascinating. So think of it like this. You have some parts of the brain that are kind of like the brakes.
Okay.
They stop signals from firing off all willy-nilly, right? Those are your inhibitory neurons.
I see. So our brains have these like brakes, but how does that explain like why the network suddenly starts combining words?
Okay, so imagine you have one brake stopping another brake.
Okay.
What happens?
Well, I guess the signal gets through. Exactly. The signal gets through. That's disinhibition in a nutshell. And in the network, those negative code values, they seem to be doing something very similar. They're like releasing the brakes on certain connections, and that allows the network to explore all these new possibilities, like combining words.
So it's like those negative values are giving the network a little push,
Yeah.
encouraging it to try something new. Yeah.
Exactly. Step outside its comfort zone. And this isn't just some random AI quirk. This actually has a parallel in how our own brains work. Remember how we talked about segmentation?
Mm-hmm.
That ability to break down a stream of sound into individual words. Well, research suggests that inhibitory neurons play a key role in that process, too.
You mean those same brakes that are getting released in the network?
Mm-hmm.
But how can stopping signals actually help us understand language?
I know, it seems counterintuitive.
Right.
Yeah, but those inhibitory neurons are crucial for filtering out all the noise and highlighting the important parts of speech. They help us create those boundaries between words, even when, those boundaries aren't super obvious in the actual sound waves themselves.
So it's like they're helping our brains carve up the soundscape into these meaningful chunks.
Exactly. And once you have those chunks, those individual words, well, you can start playing around with them, right? Combine them in all these different ways. And that's where you start to see the vast potential of language.
Wow. That's amazing. So this disinhibition thing, it's not just some technical detail in the network. It might actually be pointing to like a fundamental mechanism in how our brains learn language.
It really could be.
But if this is how we learn language, why don't we all just walk around talking like those early networks with all those like suit your kind of combinations?
Well, that's where things get even more complex.
Okay.
And this is where this research starts to raise some really, really interesting questions. Because it seems like disinhibition, that might be just the first step.
The initial spark.
Yeah, the spark that sets the language engine in motion. But there's a lot more going on in our brains that shapes how we learn and use language.
Okay, like what else might be going
Now,
on?
think about all the feedback we get as we're learning to talk.
Right.
We're constantly interacting with others, getting cues about, what makes sense, what sounds right, what gets our point across.
So it's not just about mimicking sounds, it's about figuring out how to use language to actually communicate.
Exactly, to connect with other humans. And that social aspect of language learning is something that's really hard to, replicate in a computer model.
That makes sense, but still, it's pretty mind-boggling to think that these networks are spontaneously doing some of the same things that, babies do when they're learning to talk. I mean, what are the implications of that? Like, where could this research lead us?
I mean, the possibilities are really exciting. Imagine being able to create AI systems that learn language more like humans do. Systems that understand not just the words themselves, but all the nuance, the emotion, the context.
So we're not just talking about, robots that can like recite facts or follow instructions. We're talking about AI that can truly understand and even generate human language.
Exactly.
Wow. That could revolutionize so many things.
Absolutely. I mean, think about more natural and intuitive voice assistants, seamless language translation, even AI that can help us unlock the secrets of, ancient texts or decipher languages that are no longer spoken.
Those are some seriously cool possibilities. But I have to admit, it's also a little bit daunting too. Like, if we can create machines that can communicate like us, what does that say about, our own unique abilities?
That's a big question, one that philosophers and scientists have been pondering for centuries.
Right.
As we push the boundaries of AI, it's crucial to think about not just what we can do, but also what we should do. What are the ethical implications of creating machines that are so similar to us in their ability to communicate? These are questions we really need to grapple with as we move forward.
I'm also kind of curious about the flip side of that coin. Could this research actually help us better understand our own brains? Like, could studying these networks give us insights into, conditions that affect language? like dyslexia or aphasia?
That's a really, really intriguing possibility. By studying how these networks learn and, sometimes struggle with language, we might gain a deeper understanding of the brain processes that are involved in human language, and also the challenges that arise when those processes go awry. And that could potentially lead to new therapies or interventions to help people with language disorders.
It's fascinating how this research is kind of blurring the lines between artificial intelligence and our own intelligence. It's making me wonder, like, is there really that much of a difference after all?
That's a question that's becoming increasingly relevant. As AI becomes more and more sophisticated, this research, with its focus on spontaneous concatenation and disinhibition, it's just one piece of the puzzle. There's another aspect of the study that I think you'll find particularly interesting. It delves into the idea of imitation as a driving force in language learning, both for these networks and, potentially for humans as well.
All right, so we've talked about disinhibition,
Hmm.
but you mentioned there's another piece to the puzzle, this idea of imitation.
Yeah.
I mean, it seems kind of obvious that, like, we imitate when we learn language, but is there something deeper going on here?
It might seem obvious at first, but think about it. When we're babies, we're just bombarded with this constant flow of sound.
Yeah.
And it's through imitation, by trying to copy those sounds, especially the sounds we hear from our caregivers, that we actually start to make sense of it all.
Right, so we're like, little parrots, just
Yeah.
repeating everything we hear. But how does that lead to, like, actually understanding and using language?
Well, it's more than just parroting. It's about picking up on the patterns, the rhythm, the intonation of speech, the way that sounds are combined to create meaning. We're basically internalizing the rules of language through this process of imitation.
So this is not just about, like, copying individual sounds. It's about absorbing the underlying structure of language.
Exactly. And that's what's so intriguing about these GANs. Remember, they're learning by competing, right? They're trying to generate speech that's basically indistinguishable from human speech. And in that process, they're not just like copying the data, they're actually discovering those same underlying structures, those rules of syntax, all through this process of imitation and innovation.
That's wild. So
Yeah.
they're learning to speak in a way that's similar to how we learn to speak. But how does innovation fit into all this? I mean, we're not just mindless imitators, right?
Absolutely not. I mean, think about kids learning language. They don't just repeat what they hear verbatim, right?
Right.
They experiment. They play with language. They come up with new combinations, new ways of expressing themselves.
So it's kind of a back and forth. Like, we imitate what we hear, and then we riff on it, try out new things.
Precisely. And it's in that creative space, that interplay between imitation and innovation, that language truly comes alive. And it seems like these GANs might be tapping into that same creative process.
It really makes you rethink, how we view language learning. It's not just about, like, memorizing rules or vocabulary. It's this dynamic process of mimicking, experimenting, creating. It kind of makes you wonder, is it this ability to imitate, to learn from others, that really sets us apart? Like, what makes human language so unique?
It's a very tantalizing possibility, and it begs the question, could we leverage this understanding of imitation to create even more human-like AI? AI that can not only process language, but truly understand it? AI that can use it creatively and even, generate new forms of expression.
That would be incredible.
Yeah.
But it also raises some pretty big questions. If machines can become that good at imitating us, at understanding and generating human language, I mean, what does that mean for our own sense of identity, like our place in the world?
Those are questions we can't shy away from. As we delve deeper into the mysteries of language and the brain, we need to be mindful, like, what are the ethical implications of our discoveries? What's the potential impact of creating machines that can communicate like us?
This whole deep dive has been such a trip. We've gone from the technical intricacies of neural networks to the philosophical implications of AI, and it's all been tied together by this amazing research on spontaneous concatenation and the power of imitation.
Yeah, it really highlights how much we still don't know about language and the brain. But each new discovery, each step forward, it brings us closer to understanding this fundamental human capacity, this gift that allows us to connect with each other, to share our thoughts and feelings, to shape the world around us.
It's a good reminder that even in this age of advanced technology, there's still so much mystery out there, so much wonder to be explored. So keep questioning, keep exploring, and most importantly, keep talking. You never know what amazing discoveries are waiting just around the corner. Until next time, fellow deep divers.